we'll be seeing how to find the kth smallest element in a binary search tree and build a solution in JavaScript while also computing the time complexity and space complexity of the solution that we will be building. Before jumping into the solution, let's understand the problem statement. We will be given a binary search tree. The characteristics of a binary search tree is that given a node, on the left side, the node will have a value lower than the value of the node, and on the right side of the node, the value will be greater. And this will be applicable throughout the entire tree that we are given. And we need to find the kth smallest element in this. We will be given a k value and we have to find the kth smallest element that is there in this binary search tree that is given as an input. For instance, let's say we have this tree given to us. If I sort this in ascending order, I get 1, 2, 3 and 4. Out of this, the kth index, and this binary search tree kth index is going to be 1 indexed. Basically, the index is going to start from 1 rather than 0. So when I say 1, this is the index that I'll be looking for. At position 1, we have a value of 1, and that's the kth smallest index. So we will say the first smallest index that you can find here is going to be this, and that's the core of the problem statement. To reach a solution, we will be using in-order traversal and doing a depth first search. What does in-order traversal mean? It means that we will first go and visit the left node of a specific node. Then you will go and visit the node itself. And after that, you will go on the right side and visit the right node. And we are going to maintain this order of traversal throughout the tree when we do the traversal. And how that will work is something like this. We will basically start with the root node that we are given, let's say 3, and we will go on the left side immediately without checking what this value is for the node. On the left side, we will see we have a 1 here. We will again go on the left side of this one also. So I will go on the left side. I don't see anything on the left side of this one, and I did this left side check. Then I have to come to the node itself. So for the node, I have a value of 1. This value I will keep track using an array. I will put it in my array and move on. After visiting the node here, I have to go to the right. So I will visit the node, I put it in my array. I will now go to the right. On the right, I see this 2 here. Now this 2, I will again go on the left side. First, I don't see anything on the left. Then I will come to this 2. So I went to the left, I went to 2 itself. I will put 2 in my array. Then I will try to go on the right side for this 2. I don't have anything on the right side also for this 2. So now I will backtrack. I will go back from here to here, and then I will go back to my root. So the logic of visiting the left has now been completed. Then we see what this node value is. The node value is 3. I put it in my tracker array. Then I will go on the right side. On the right side, I see this 4. For 4, I will again try to go on the left side. I don't have anything on the left side. So I will come back to 4. I will put this 4 in my array, and then I will try to go on the right side, which doesn't have any value. And I have reached all the values in the tree that I'm given, and I stop here. And I have this array which got created while I was doing this traversal. From this, I will just pick the kth element, and this is going to be 1, and return it. And that's pretty much it in terms of the logic aspect of it. Let's convert whatever we covered so far into code. We said we will be keeping a tracker to keep track of the elements that we are visiting. So I will just say let nums is equal to empty array, and in the end I will basically go through my nums array and I will return k minus 1th element, because we have to find the kth index, but k is starting from index of 1. So that's why I will do k minus 1. So if k is given as 1, 1 minus 1 is the 0th index, basically the first value in our array. And we also said that we will be doing a depth first search in a in-order traversal approach. So for doing that, I will just keep saying let const dfs be a function, and this function is going to do a in order traversal. So I will just say in order DFS. I will just take a node for this function and perform some operation, and I have to also make sure that I trigger this DFS mechanism, because for DFS I will be going into recursion. So the recursion is going to have two elements. One is the trigger point and another is a exit condition along with the logic that we have. And to trigger it, I will just say DFS, whatever route I am given, I will just pass that route to perform the depth first search. After this, I will go inside my DFS function. I will check that if my node is going to be null, then I just return, because in the case of reaching this node 1, I went to the left, I had nothing here, so then I have to backtrack from there. So to backtrack, I just return. Then after this, what we are going to be doing is follow this in order traversal pattern, wherein we said go to the left node first, then come to the root, and then go to the right node. And to do the depth first search on the left node, we can simply say do this DFS using the node dot left node that you have. After that, you want to see the current root value that you have, and you put this root value in your tracker array. And to do that, I am just going to say nums dot push whatever the node value I have. The node value I have is going to be node dot value itself, and I visited the left node using this depth first search. I find the value of my node, which will now go in the tracker that I'm keeping via this nums array. And after this, I have to go also to the right node. So to do that, I will just do node dot right, and this will complete my in order traversal mechanism to be used here to go first to the left node, then to the node itself, and then to the right side of the node. And that's pretty much it in terms of implementation that we have here. We just started from this empty tracker, we iterated and created this array that we wanted and put all the values of the nodes that you traversed in the order of your traversal, and then you just return nums of k minus 1, which gives you the value at the specific index which you are looking for. Now in terms of the time complexity that is going to be involved here, it's going to be big O of n, because we are going to iterate through the entire tree that we are given in a depth first search fashion. That's why the time complexity is also going to be big O of n. And in terms of the space complexity that we have, that is also going to be big O of n, because the calls that are going to happen recursively for each node are going to be put on the call stack, and that call stack is going to occupy space for the nodes that we have, and then we will just return, and after returning, the pop happens in the call stack. So because of that, the space complexity will also be big O of n. We can now go a step further and try to see if we can optimize the solution that we have built. So the first approach we said is we will be using this data structure array and try to put all the elements as we traverse to them and try to build the structure with this array and return the index by picking just the value from the array. What if we just keep a tracker? I will just modify this and say just keep a count, and let's initialize it to 0. And I will see if I have a result which can possibly not exist. And I will also say that in the end, just return my result, whichever I have found. Now, what I will do is, instead of pushing in my data structure array, every time I come to my root, I will just increment the count that I'm at. And if the count is the kth index count, then I have found the kth smallest value, because the traversal itself is happening in the in order sequence, because I'm going to the left, then I come to the value, and then I'm going to the right. And when I come to the value, what do? I will just check if my count is going to be equal to k, which means I have found my kth smallest element. I will just set my result to whatever value I have with me at that point of time, which is going to be node dot value. And then with this value, I will set my result and I will just return from the function that is going into recursion. Now, to optimize the solution, what we can do is make sure that we do this depth first search in a recursion manner until you find your k. After you find your k, you just exit this recursive callback that happens. And to do that, I can put another check in my exit condition, and that check can be something like saying if my result has been found. That basically means result is not null anymore. Then I just return from the function that I have. And this way, I will go only up to the k elements when k is very small. In the best case, the time complexity that is going to be required is going to be big of k. And similarly, in terms of the space complexity, that also will be big of k, because then once I find my k, I will not be going into further recursions. I will just be returning. And that's the optimized approach. But in the worst case, when you have k at a very high index, then it will be big of n itself, both the time complexity and space complexity, because the time complexity and space complexity are directly affected by the depth within which we are going and how many depth first search calls are going into this call stack. And that's pretty much it. Thank you for watching. Please like and subscribe.